Hi, this is the last video on hypothesis testing. In this video we're going to look at two-tailed tests. Okay, so one-tailed test, just to remind you, is used to test when it is claimed that the probability has either gone up or gone down. So if you suspect the probability has gone up, then last time we were using an alternative hypothesis that P is greater than whatever the probability is. Okay, or you might suspect that it's gone down, in which case the alternative would be P is less than something. Okay, a two-tailed test is used when it is thought that the probability has changed, but in either direction, so we don't necessarily know how it's changed. In that case, we write our hypothesis as P is not equal to. So if you see that, then you know you are doing a two-tailed test. So if you are doing a two-tailed test, then what we need to do potentially is work out two regions. On these ones, we worked out one critical region. Either the critical region was at this top end, close to 10, so let's say n equals 10. The critical region might have been greater than 8, or greater than 9, or greater than 10, or equal to 10. So at this end, if it's greater than, or the critical region might have been something down here, less than or equal to 2, or less than or equal to 1, if it was like this. Okay, that's why it's called tail, because if you think of the number line, we're either at the top end, the top tail, or we're at the bottom end. If you are doing a two-tailed test, then there will be two critical values that we may need to consider. And in some questions, you need to find them both. In other questions, you might only need to find one. And the circumstances where you might only need to find one is if you are given a test statistic. So if your test statistic is less than the expected outcome, then you really only need to consider the lower end. If your test statistic is greater than your expected outcome, then you really only need to consider the top end. If you don't have a test statistic, then we are going to have to find both of these. Okay, so just to show you that, I'm going to work through 4 or 5 examples. Now for consistency, I'm going to work out the critical region or the critical regions first, even though I've got a test statistic, because these questions can get slightly more complicated, so I'm going to use the same approach each time. Okay, first question. A single observation, x, is taken from a binomial distribution and a value of 10 is obtained. Use this observation to test h0, p is 0.5 against h1, p is not 0.5. Okay, so the first thing you should notice is that there. That tells you that you are doing a two-tailed test. Okay, we also have a 5% significance level, and we also have this number here, which is a test statistic, and I will use that later on. Okay, so let's write a few things down. X is distributed binomially, number of trials 30, probability of success is 0.5. H0, P is 0.5, H1 P is not 0.5. Okay, we're doing a 5% significance level and it is two-tailed. Okay, let's work out our expected outcome. Expected outcome is number of trials times by probability of success, which in this case is going to be 15. Okay, I'm just going to draw a number line. So there are 30 trials. The expected outcome is 15. This is the default probability, and we are looking to see if actually that probability is not 0.5, it's something else. Okay, so potentially there are two critical values. Critical value and a critical value. There is a number here whereby anything less than that would fall in our critical region here. So this is our critical region. Critical region. So there's some value here whereby anything less than that would fall in the critical region, and if our test statistic lies in that critical region, then that will be enough evidence to reject that. There is also another critical value here at the top end, whereby anything greater than that would fall in our critical region, and if our test statistic falls in that critical region, then we could reject that. So there are, because we're now looking at a two-tailed test, we're looking at values close to 0 and also values close to 30. So potentially we need to work both of these out. Now then, because we have a test statistic of 10, well, that's less than the expected outcome. So it's potentially only going to fall in this region. So we don't really need to bother. It's not going to be up here. So we can ignore that. We don't need to bother working that out. So because we know our test statistic is less than expected, we only really need to consider this bottom end. Now, because we're doing 5%, on one-tailed tests, all of these probabilities add up to 5%. But because it's two-tailed test, all of these probabilities have to add up to 5%. So these probabilities need to add up to 2.5%. So when we are doing a two-tailed test, we need to halve the probability and compare it to that. So we are going to look for what our critical value is here. So the probability that x is less than or equal to something now has to be less than 2.5%. Okay, so let's stick some numbers in. I'm going to start with, let's start with 8. So if I type in 8 and 30 and 0.5, I get something really small, 0.0081. So I'm just going to go a bit higher. Less than 9. That is, 0.0214. So now I'm just going to go for 10. See what happens if I put 10 in. That is 0.0494. Now I'm just going to put 11 in. That is 0.100. Okay, so this one, didn't really need to do that one, did I? This one is our highest value here that goes below 2.5%. Okay, so 0.0214 is less than 0.025. Therefore, the critical region is x is less than or equal to 9. Okay, so we've identified the critical region. Now then, we have our test statistic. So we now know that this is 9. And our test statistic does not fall inside that critical region. Because that test statistic doesn't fall inside that critical region, that means we cannot reject that. There is not enough evidence to suggest that the probability is not a half, that it's different. Okay, so I'm going to just write 10 is not in the critical region. Failure to reject H0. Okay, so I've worked out my value, I've shown my calculation, I've compared my probability to the significance level, which I've halved, I've got my critical region, and then I've stated whether my test statistic is or not in the critical region. In this case, it's not in the critical region. So because it's not in the critical region, I cannot reject H0. Okay, there is not enough evidence to suggest that the probability is not a half. Okay, let's try another one. A random variable has distribution x distributed binomially, number of trials 25, probability p. A single observation of 10 is taken from the distribution, test at a 10% significance level that H0 p is 3, H1 p is not 3. So two-tailed, 10% significance level, test statistic. Okay, so x, squiggle, b, 25 and 0.3. H0, p is 0.3. H1, p is not 0.3. 10% significance level, two-tailed. Okay, so if we work out the expected is going to be 25 times by 0.3, which is 7.5. So our test statistic is bigger now than the expected. So we only need to consider if our expected is 7.5, 10 is going to be somewhere up here. So we only need to consider this end of our number line and not the lower end. So it is two-tailed. We are going to have that significance level, but we only need to consider it at one end. So we only need one critical value. Okay, so probability x is greater than or equal to r this time, because we're looking at the top end, that's got to be less than half of the 10%, which is 5%. And don't forget, we have to do that. So that's our statement. That's what we're looking to try and show. So if I choose some numbers, so let's go for, I don't know, I'm going to start with 15, 25 and 0.3. So 1 minus probability that x is less than or equal to 15 is 1 minus 0.9995, which is 0.0005. So I need to go smaller than that. So I'm going to try 13. X is less than or equal to 13 is 1 minus 0.994, which is 0.006. So I'm going to try lower than that. 11. So 11 will be 1 minus 0.956, which is 0.044. Okay, I'll just double check and put 12 in. No, that's 0.02. Okay, better just double check and put 10 in. That's 0.1. Okay, so this one is the one that's closest and just under 0.05. So r minus 1 equals 11, therefore r must equal 12. So the probability that x is greater than or equal to 12 is 0.044. Therefore, the critical region is x is greater than or equal to 12. So this value here, this is 12. Looking at our test statistic is 10. That does not fall inside that critical region. So it's the same conclusion as before. 10 is not in the critical region, therefore failure to reject H0. Okay. A coin is tossed 20 times and lands on heads 6 times. Use a two-tailed test with a 5% significance level to determine whether there is sufficient evidence to conclude that the coin is biased. So this is where we need to interpret the words. A coin is tossed 20 times. So that's n is 20. And lands on heads 6 times. That is our test statistic. Two-tailed test, 5% significance level to determine whether there is sufficient evidence to conclude that the coin is biased. Okay, so we're concluding that the coin is biased. It doesn't say in what way, which is why it's two-tailed test. Now that question could have missed out that word. It could have just said you do a hypothesis test. You would have had to realise from the wording that it means two-tailed. So just be careful when you read it. So we're initially assuming that the coin is fair, and our alternative hypothesis is that it's not fair, that it's biased. Okay, so make sure you write down your hypotheses, make sure you write down your binomial information. We can work out then our expected, so you would expect to get 20 times a half, so 10 heads, and we have got 6 heads to test. So on our little number line, from 0 to 20, the expected is 10. We're doing two-tailed, so we've got 2 critical values. But because we are going to test whether 6 is in a critical region or not, we don't need this one. So this is the only one that we're interested in. So we're going to do probability that x is less than or equal to r. That's our critical value. That's got to be less than half the significance level. So 0.025. So let's start with, I don't know, 7. See what happens. X is 7, N is 20, P is 0.5. That is equal to 0.132. So we need to go smaller. Let's say X is less than or equal to 6. That's 0.058. Let's go to 5. That's 0.021. Okay, that is the first one that's gone below 0.025. Okay, so 0.021 is less than 0.025. Therefore, the critical region is X is less than or equal to 5. Okay, so we would need to get 5 or less heads for there to be enough evidence that the coin is biased. Okay, so this is 5. So 6 heads does not lie in that critical region, so therefore there is not enough evidence to conclude that the coin is biased. Okay, so we need to write that down. So 6 is not in the critical region. Failure to reject H0. Not enough evidence to conclude the coin is biased. Okay, so I've done, so binomial information, 1 mark, hypotheses, 1 mark, expected value, 1 mark, calculations, 1 or 2 marks, depending on what they want, 1 comparison, 1 critical region, 1 conclusion about the test statistic with regard to the critical region, 1 conclusion about the null hypothesis, and in this case 1 conclusion in the context. Okay, you cannot skip any of that out, otherwise you're just throwing marks away. Okay, tests have been carried out on a pupil who wants to improve her short-term memory. Over a period of several weeks, the pupil has repeated a test and remembered on average 35% of objects on a tray. After a short break, a further test is carried out to see if there has been any change. Find the critical values for a two-tailed test using a 5% level of significance. Let X be the proportion of objects the pupil has remembered. Okay, so let's start with this. X is the proportion of objects the pupil has remembered. So this is like n, the number of trials. If it's representing a proportion, then n is going to be 100. The pupil has repeated the test and an average 35% of objects on a tray. This is P. So P is 0.35. After a short break, a further test is carried out. We don't know what that pupil got in that test, so that we do not have a test statistic, but they want to see if there has been any change. So we don't know if the change is up or down. It doesn't specify, which means that we are on a two-tailed test. Okay, it does tell us. 5% level of significance. Okay, so because we don't have a test statistic, we are now going to have to work out two critical values. So from 0 to 100, the pupil is getting on average 35 of them correct. Okay, so there is going to be a critical value down here, and there is going to be a critical value up here, where any number in here and any number in here would tell us that there has been a change. Okay, so what we're asked to work out is these two values, what these critical regions is. So for this one, we want the probability of X to be less than or equal to R, and I'm just going to call this R1, to be less than 0.025. Okay, and for this one, we want the probability that X is greater than or equal to R2 to be less than 0.025. Okay, so I'm just get rid of that, because I can't remember why that's there. So I'm just going to call it R1 and R2 for the two separate critical values. Okay, so for this one's a bit easier. Let's test something, so maybe let's start with, I don't know, 20. N is 100 and P is 0.35. That's tiny, I'm not even going to write that down. So let's go for 25. Okay, probability X is less than or equal to 25 is 0.0211. I'm just going to explore either side of that just in case. So 26. 26 is 0.035. So this is too much, so this is the one we want. Okay, so 0.0211 is less than 0.025, so therefore the critical region X is less than or equal to 25. That's the easy one, easier one. This one, because it's greater than, we need to remember to do this. So we need to take one off. Okay, so let's start off with 70, I'd guess. Oh, that's 1, so we need to come down. I'm not going to write that down. 60, that's very small. 50, so 1 minus the probability that x is less than or equal to 50 is 0.0007. So I'm going to try 45. 1 minus probability that x is less than or equal to 45 is 0.015. So we're getting close. If I try 44, 1 minus 44 is 0.025. So 0.0247 to be precise, a bit closer, a bit more detailed. So that is the one. So 0.0247 is less than 0.25, therefore the critical region is X. Oh, sorry, what I should have said was R minus 1 is 44, therefore R is 45. So the probability that X is greater than or equal to 45 is 0.0247. Therefore, the critical region is X is greater than or equal to 45. So, in the context of the question, the pupil would have to remember 25% or less, or 45% or more, for there to be seen to be a change in her short-term memory. Okay, so that's what that means. If we were then given a test statistic, so let's say we found out then that she'd remembered 60 objects, then we could say that that falls in that critical region, therefore there's been a change. Or she might have remembered 10 on the next one, in which case we could say that falls in that critical region, in which case there's been a change. Or she might have remembered 40, in which case that doesn't fall in any critical region, in which case we could say that there's been no change. Okay, so they could potentially then ask you or give you a test statistic for you then to work with. Okay, now this is a little slightly different, and there's some red writing. Take care with significance level, read the small print. So I've put this on purpose. The proportion of defective articles in a certain manufacturing process has been found from a long experience to be 0.1. So this is our p-value. A random sample of 50 articles was taken in order to monitor the production and the number of defective articles recorded. So n is 50. Using a 5% level of significance, find the critical regions for a two-tailed test of the hypothesis that 1 in 10 articles has a defect. So this is our 0.1. The probability in each tail should be as near 2.5% as possible. Okay, so we're doing 5% two-tailed test, but this is the small print. The probability in each tail should be as near 2.5 as possible. Now, because it says that, it means that potentially one or both of them could be over 2.5%. It's just got to be close. Okay, so they don't, in this case, they're not necessarily looking for the one that goes below 2.5%. They're looking for the ones that are closer to 2.5%. Okay, there may be questions where they ask you for the combined percentages to be as close to the significance level as possible. In which case, one could be over and one could be under, but together they add up to the significance level. So you're just going to be really careful when you're doing these two-tailed tests about this small print. Okay, so we've got x is distributed binomially, that's 50, and that's 0.1. Got the null hypothesis is that p is 0.1, and the alternative hypothesis is that p is not equal to 0.1. We're doing a 5% significance level, and it's two-tailed. And we're looking for both the regions, so finding the critical regions. So same as last time, same as the last one, we're going to have one where we want the probability that less than or equal to one critical value has got to be less than, or in this case, as close to 0.25 as possible. And then the other one, greater than R2, has got to be less than, or in this case, as close to 0.25 as possible. Okay, so let's stick some numbers in. So I'm going to start off with a guess of 10. See what happens. So 10 is far too big. So I don't know why I even bothered writing that down, to be honest. So let's go smaller. I'm going to go for 1. 1 is 0.0338. 0, the only one I can do, which is smaller than 1, is teeny tiny, 0.0052. So the one that's closest to 0.25 is this one, I think. Yeah, this one. Okay, so even though it's gone over, this is closer to that than that. So in this question, they want it to be close. This one, remember we need to do this. So we need to take it away from 1. So let's start off with 45, far too big. 40, too big. 30, too big. 25, 20, still too big. 15, still too big. 12, 1 minus x is less than or equal to 12 is 0.001. I'm going to go smaller. Let's change to 11. 11 is 0.003. 10 is 0.009. It's moving very slowly. 9 is 0.0245. And I better just check that 8 doesn't go close over, but closer. That's 0.0579. Okay, so that was gone over, and this one's closer. So this one here is the one we want. R minus 1 is 9, which means R is 10. So the probability that X is greater than or equal to 10 is 0.0245. Okay, so our critical regions are X is less than or equal to 0, and X is greater than or equal to 10. Okay, so it's more work, having to explore a few more numbers, but you've got to be careful. Okay, so just because it's gone over doesn't mean that's not going to be the one you want. Okay, now for part B, it says state the actual significance level of the above test. Remember, the actual significance level is the probability or the chance of wrongly rejecting the null hypothesis, and that comes from the probabilities. So we have used that probability there and that probability there. So the actual significance level, so it's not 5%, is going to be those two things added together, which is going to go over 5%. So 0.0338 plus 0.0245 is 0.0583 or 5.83%. That is the actual significance level. So the percentage chance of wrongly rejecting the null hypothesis if we were given a test statistic. Okay, so just be careful with those small prints. So sometimes if it doesn't say anything, if you're looking for both regions and it doesn't say anything, then you look for the two that go below 0.25 like I did in that question. Okay. Otherwise, look for specific information. So it may want each tail to be as close to, in this case, 2.5%. It may want the combination or the total of the two probabilities to be as close to the 5% in this case. Okay, so you've just got to be really careful. In that case, one might go over and one might go under. Okay, so we've covered the whole of hypothesis testing now, so you should be able to hopefully have a go at some of those.